I just want to point out that the first speaker is here live from Parma, and the other ones will make the presentations remotely. So I give the floor to Marco Gavanelli, which is the chair of this session.
Hello, everybody, and welcome to this session. So, as you have heard, we have a talk which is given directly from Parma, and this talk is about convergence verification of declarative distributed systems, and it is a work by Diego Calvanese, Francesco di Cosmo, Jorge Lobo, and Marco Montali. And I guess Francesco is giving the talk. Please, Francesco.
So, thank you very much. I'm very happy to meet you all in person, almost all of you in person, here in Parma. I'm Francesco, student, PhD student at Delzanno, and I would like to share with you my latest work in my research project that is about verification of declarative distributed systems. That is a model or a formal model of distributed computation grounded in logic programming. These kind of models were motivated by the area of declarative networking, that is the development and implementation of network protocol and services by means of declarative languages. In fact, the declarative approach in distributed systems is really interesting for at least 3 reasons. It allows for very short implementations of programs, and thus programs that are easier to debug. It allows to focus on what you want to achieve with your system instead of how you want to achieve it, and so it simplifies even more the implementation. And finally, it allows for a very strong correspondence between the actual system and its formal representation, on which to apply, for example, formal models, methods. In fact, in our work, we want to provide a rigorous and systematic study of model checking techniques for these kind of systems. In this diagram, you can see how a DDS is made. It is basically a network of intercommunicating nodes. Each node has at least a self loop to simulate communication with himself, and channels can be of 3 types. Can be, as usual in distributed settings, scenarios, perfect, if we cannot lose messages during communication, and the sending order is the same as the reception one, lossy or unordered, as the name said. We consider in this presentation, however, only uniform networks, so all channels must be of the same type. This is just to make the system a little bit simpler. Locally, each node can be seen as a data-aware process. That is a process that only manipulates relational data. So specifically, each node has a program written in the datalog-like language D2C, as a memory that is modeled by a state database over a state signature. And this memory also accounts for some topology property, namely the name of the node and the name of all its neighbors. Moreover, the node can interact with external services by receiving input databases over an input signature. There are many input policies that can be considered. Here, we consider the one that is called interactive. That is, at each step, the node can receive a new, fully random input database. For what regard communication, nodes can share messages one with the other, and messages in this setting are just single relational facts over what we call a transport signature. The reception of such a fact triggers the node activation, and the node will evaluate its program over all of these information sources that will result in a new state database and in a set of outgoing transport facts that are sent to the respective node neighbors. Here we have an example of that language D2C, and as you can see, it is an extension of datalog with stratified negation. The new features are this head symbol that allow us to perform message passing when it occurs in the head, for example, In the second rule, it means that when we deduce that head, we have to send the join fact to the node n, and when it goes in the body, it just asks us to check whether we are receiving that message. And with that prev operator, we are able to query the previous configuration of the state database. However, these operators are just syntactic sugar, so we could recast all of these in standard data log with certified negation. An additional feature of this language is that it also supports non-deterministic transitions. By means of that choice operator in the manner of Sakai and Zaniolo, we are able to enforce non-deterministic functional dependencies between the variables in the views during evaluation. And this operator is very interesting because, for example, it allows us to also to remove that variable x, so we can write also choice y, and it allows us to perform a functional dependency with trivial domain, so to select only one constant from all possible bindings of y. And this choice operator is also very interesting because it retains polynomial evaluation of this language. So the DDS semantics is given by what we call distributed relational transition systems, because those systems are, at the end of the story, just dynamic systems over data. And usually their semantics is given by transition system in which the configurations are labeled with single databases. However, here we have to account for two dimensions. The configuration of the nodes, that is a simple database, so no problem, but also the configuration of the channels. And according to the assumption that we make to the channels, it may be the case to model them with an instance of a specific data structure of a different nature. For example, as usual, for perfect channels, it is okay to model them with queues. So there is an order, first in, first out. In case of unordered communication, it is better to consider multisets. In fact, in this presentation, I will talk only about multisets because it is known as a general principle that in distributed systems, in verification of distributed systems, perfect channels on their own without data are enough to provide undecidable verification. So we deem that the interesting case is that of unordered communication. So we take these configurations, we label them with all of these configurations. And however, this is just, again, syntactic sugar. It's just a matter of formality, because in case that we can model those instances of channels by means of a database, we can just take, for example, the disjoint union of all these informations and obtain a standard system. For what regards verifications, we focus on convergence properties. Convergence is a generalization of termination and asks whether we can reach a configuration in which, from that point forward, the state configurations of the nodes will never change anymore. So we can still have messages on the channels. We can still send messages over them, but our internal representation of our state will never change anymore. And moreover, since we have to deal with this non-determinism coming from the input database, we wanted to equip the nodes with a mechanism to signal when the node has entered in a narrow state. For example, if a user provides a bad form input, or if some unexpected message is received. And by mixing convergence and correctness, we obtain these four properties, that is sometimes or always convergence, that asks whether there is one run or all runs reach the convergence configurations, and total partial correctness regards how many nodes are in a narrow state. Total correctness means no node is in error, partial, at least one node is in error. However, in the case of single node network, so one node with a self loop, total and partial correctness are just the same because there is only one node. Remarkably, all of these four properties are expressible in sophisticated verification languages that mix first order for query the state of the channels and the nodes, and CTL to address the evolution of the system, the temporal evolution. So, can we perform verification? Is that problem decidable or not? As a rule of thumb, since we are facing possibly an infinite amount of data coming from the input, we are dealing with infinite transition systems, and usually this is a source of undecidability. So our idea was to consider bounds on these information sources. So for example, state boundedness means that there is a constant B such that at each possible snapshot, for each possible node, the state database, its active domain, is bounded by B, can contain at most B constant. As usual in distributed system, channel boundedness instead means that channels can contain at most B messages, and it indirectly also bounds the active domain. And finally, we have also input boundedness that is the same as the other state boundedness, but on the input database. Notice, however, that while the first two are a consequence of the program, so a system can be bounded or not, channel and state bounded, while input boundedness is a choice on the input policy. So to have an input bounded system means to change a little bit the input policy. And so we consider, to begin, the case where all these information sources are bounded. What do you think? This case is decidable or not? Alessandro? Yes, in fact, it is decidable. Why is it so? Because in the case where we have a bound on the channel content, we know that we can model in a uniform way the multisets by means of databases. And so we can recast the distributed transition system in a standard one. We can reformulate convergence into first-order CTL. And then, since D2C has virtually all query languages is generic, it means also that the resulting transition system is uniform. That means that from isomorphic configuration, you can transition only to isomorphic configuration. So you can get a finite abstraction up to isomorphisms. And then working on this finite abstraction and using that result from Belardinelli, we know that first-order CTL verification of bounded uniform dynamic systems over data is decidable. And so we can get our decidability result. But then it opens a question. The result opens a question. Are we bounding too much information sources? Can we lift at least one of these bounds? And so we moved on by lifting state boundedness. Is this case decidable or not? Who wants to try to give an answer? So someone thinks that it is decidable, but actually it is not, sorry. The reason why it's not decidable is that because we can provide a reduction from termination of two counter machines, that is an undecidable problem, to convergence properties of single node DDSs. Two counter machines are roughly finite state machines on which we have counters, two counters that are able to count and can perform increment, decrement, and zero checks instructions over them. And we can, and since we have an unbounded input, we can encode these counters inside states by a single unary predicate counter, for example. We can check whether it is zero very easily because we have a full availability of this information. To perform an increment, we have to read the input that is bounded, but at least one constant should be available. Check whether this input is fresh with respect to the counter. If it is not, we deduce an error. If it is, we put it in the counter, and so we are returning it. To perform a decrement, instead, we can use this choice operator to randomly select a constant from the counter, and then basically remove it from it. And so we have these three ingredients, and combining them in the right way, we can simulate the original two counter machines up to error. And since we have convergence up to error, the convergence properties are equivalent to the termination, so we have undecidability. The same idea can be adapted also when we have only unbounded channels. And the idea here is to encode the counters inside of the channels by means of by these digraphs, cyclic digraph, in which one node has a special role, and its name, because it's a constant after all, is memorized in a persistent and read-only way. For example, it could be the name of the node. And the reason why we can make again all these recast all these ideas is because even if the channels are unordered, by exploiting the data, we can act as these channels are actually ordered, because it is sufficient to just remember the last constant seen in the last edge and to compare it with the first constant in the next edge, as is seen in the animation. In case these constants are the same, it means that we are receiving the edges in the right order. Otherwise, it means that a disorder has occurred, and so we can deduce an error, and so we can continue as seen before. And so we have undecidability also here. The last case is that of unbounded input, but bounded channels and state. So this means that even if at each step we can receive only B constants, during the whole evolution of the system, we can still see an infinite amount of data. Is it right? No, that was before, sorry. In this case, we can receive an infinite amount of data at each step. So is this case decidable or not? This case actually is decidable. And the reason because it is decidable is that since the state and the channels are the only things that are mentioned in the distributed transition system, it means that after all, when we are computing our program, we already know that we will see at most those constants deduced in the heads. And so we can fix at the beginning of the computation a fixed set active domain, I would say it's not active, a bounded domain up to isomorphism, and use it to ground the heads. Then we can also ground the state literals and the channel literals in the rules, and what remains is just a bunch of literals over the input signature, and thus the impact of that infinite amount of input databases is just to make those queries true or false. But these queries are in a finite number, and so we can build a table basically to check which combination of those queries are satisfiable or not in the finite. We can luckily check that problem because it is decidable. And then by using that finite table, we can simulate the transition, and so we are able to build a finite abstraction. So in conclusion, this table summarizes our results. We have two decidability results in the case that state and transports are bounded, and in this case, by always because of those results by Bellardinelli, we have also that the problem is p-space complete in the data complexity, so in the initial configuration of the system. That also includes the structure of the network because of how the initial configuration is made. So as future works, we would like to simulate DDSs concretely in ISP, at least for the cases of decidable verification. And here, for example, the main problem here is to treat the communication in such a way that we do not have a bottleneck, and also how to offer an infinite amount of inputs randomly to the system. However, by leveraging on the technique seen in the last proof, we deem that we can do that without even caring about the actual input database that we can see. Other directions consider dynamic topologies that can change or completely randomly or in some fixed pattern that would serve as a new source of non-determinism, and then maybe making the problem undecidable or decidable, very likely as seen in this table. And finally, other direction could be to consider other properties, classical, like safeness or liveness, for example. So if you want to read more, these are some essential references. And if you want to contact me, write to me at this email. And thank you.
So thank you, Francesco. Are there any questions, either from Parma or from people online? Alberto, I see you. Maybe you can have a question.
No, actually, no, thanks.
Oh, sorry. I just saw you appearing, and so I thought you wanted to. Okay. Actually, I would like to ask a question myself. When you talk about extending the network, so if you allow one to extend it in any possible way, probably you cannot be. It's not computable, right? So, in which direction, in which ways do you think you could restrict the modification of the network in such a way to obtain decidability?
Well, so the problem of undecidability can. So we didn't thought about that very much. The idea is that if you're allowed to have the network that grows completely non-deterministically, then you can use, for example, the size of the network as a counter. And up to errors, you can model again the two counter machines in some way. That's the idea. So I think that the problem is to constrain the evolution, to constrain the evolution of the network in such a way that we are not able to arbitrarily mimic, simulate two counter machines. And so I think that we have to make sure that the nodes have some way to decide whether to join or leave the network in a very subtle way, so that they have control on how to do this. So the non-determinism is not too much, but also this is not too much deterministic, in order to link the state and the program to the evolution of the network. Otherwise, we can use the interaction between the joining and leaving behavior of nodes to, in conjunction with the program and the state, to obtain, to recast these ideas. So the problem may be tricky, actually. We do not know it.
Okay. Okay. Are there further questions? We do not have much time. If there is a very quick question, maybe. Okay. So let's thank our speaker again. Okay, we can now move to the second talk of the day. We have a talk titled Verification of Contact Tracing Protocols via SMT-based Model Checking and Counting Abstraction. And it's a joint work by, I'm pretty sure I will not pronounce correctly the names, but I ask for an apology. I apologize for that. By Sylvain Conchon, Giorgio Delzanno, and Arnaud Sangnier.
Yes. Okay. Good morning to everyone. Thanks for the presentation. So let me share the presentation. I think the names were more or less correct. So Conchon, Delzanno, and Sangnier. And so this is it's a work that we did after some initial collaboration with Marco Montali and other people that we presented in Overlay 2020, in which there was a preliminary formalization of a family of protocols that are inspired to contact tracing procedures. So in this paper, together with Conchon and Sangnier, we try to refine the protocol specification using an automata-based language. And we also present in the paper an encoding in SMT solver that can be used in order to verify some interesting property for this kind of protocols. So in the talk, I will start from background and motivation. So I will briefly present what these contact tracing protocols look like. So how they look like. And then I will move to the model, the data automata-based model. So here, I think the interesting point is that so the model is inspired to, it's an extension of Patriot-like languages, but we consider a special kind of local variables that can also range over sets of data, so higher order variables. And then the second part of the talk, but it will be a very brief introduction to the more practical part, is an explanation of the encoding of this data automata into an array-based specification language, as provided by the Cubicle model checker. Cubicle is an SMT-based infinite state model checker that essentially exploits an SMT solver for the theory of unbounded arrays, combined with other kind of theories like Pressburger constraints, and performs symbolic exploration of the state space of the specification of a protocol. So let's say the logical language is used in order to specify sets of states of a protocol, and the solvers are used in order to compute precondition or postcondition with respect to the protocol rules. The Cubicle model checker has been developed in order to verify parameterized properties, so properties that are assumed to hold for an arbitrary number of process components. And that's exactly what we try to, so that was our focus for this kind of, for these examples of contact tracing protocols. And then I will address some conclusion, because we have some more interesting results on the let's say, expressiveness of the model, and we think that we can prove some decidability result for fragments of the data model, data automata specification language. So we are discussing this with Arnaud. We have discussed this point in the last weeks with Arnaud. Okay, so I will try to focus more on the context and less on the technical details, especially concerning the, let's say, practical verification side. So background and motivations are related to contact tracing. So contact tracing systems are designed to support the process of identifying contacts with certain individuals. So they have been, they became quite quite known for the COVID pandemic. I mean, as a support for contact tracing during the COVID pandemic, but they are used also for other classes of applications, and they are somehow similar to tracking protocols that are used for tracking, for instance, vehicles and so on. So in the example, in the setting of let's say pandemic contact tracing, so there are protocols that have been developed for smartphones, like the very well-known Immuni application, but there are also specialized devices. For instance, the Estimote company that produces several kind of Bluetooth devices has developed a specialized device for contact tracing that, as seen in the slide, can be used, for instance, for in a working environment in order to collect information about the movement of personnel and so on. So in general, these contact tracing systems are non-trivial IoT applications because they involve both devices and some kind of centralized or distributed system in order to collect the logs of the information that are produced by the devices. And in fact, there are several papers on the architecture of this system. For instance, one interesting paper is by Serge Vaudemont, centralized or decentralized, the contact tracing dilemma, in which they explain, there are many examples of, let's say, pros and cons of the different architectures. And there are also examples of architecture based, for instance, on blockchains, so completely distributed, let's say, shared memory, okay, in order to collect the logs of the devices without breaking data privacy properties. So clearly, contact tracing is a very delicate kind of application because of data privacy, and for this reason, there are many works also on cryptography in order to, let's say, protect the information of each individual. So in general, how these protocols work, let's consider a device-based protocol. So this protocol typically use Bluetooth devices. So these devices broadcast over a short distance, let's say an identifier that we assume that is valid and authenticated, and that cannot be connected to some user. Okay, so that's the central point. The identifier should not be directly connected to the user that owns the device in order to avoid the broadcasting also of the contact details of the user. Proximity between users are estimated by measuring the radio signals used by the devices, and I mean other devices of the same type, like those that I presented in the previous slides. So can be used to collect all the broadcast identifiers. Okay, so essentially it's like I mean, in some sense, the contact tracing protocols simulate the pandemic diffusion. So a device sends a broadcast in the surrounding of the physical in a short distance, the surrounding environment, and other devices collect these identifiers and store the identifiers in their local memory. Okay, identifiers typically have a short life, and when the temporal marks of the identifiers fall out a given time window, they are removed from memory. So in order to avoid to use too much memory. Okay, so typically these devices are low-cost devices, and you don't want to store all the history of collected identifiers. And then there are other phases in the protocol. So for instance, when users, in the case of pandemics, contact tracing used applied in the pandemic case, when users are diagnosed to be infected, they voluntarily can release a report to a shared server. So the shared server can be modeled in different ways. So as I said before, there are architectures that are based on centralized systems, and then you have to trust clearly the entity that handles the server, that controls the server. Or there are also approaches based on a completely distributed peer-to-peer systems in which the idea is that there is no central authority and users exchange information by using this peer-to-peer infrastructure. So, so when a user releases a report, for instance, to a centralized database system, other users can consult the log. Okay, the report can be viewed as part of a shared log, So other users can consult the shared log to check if they cross their way with infected users. So they don't know the identity of the users that they have met in the past, but they know that this user has sent the report to the server, and so they can, for instance, go to and ask for a medical check. Okay. So if a contact is found, the user must register again to re-enter into the system in order to avoid to restart after, for instance, recovering from the disease. So that's more or less this is the idea. So you see that we have devices that broadcast identifiers in a short distance. They have to communicate information to some, let's say, central or distributed entity that stores these logs. And then other users can, or other devices can query this information in order to retrieve information from the log. So more or less, these are the main ideas of this kind of protocols, but there are many variations of the protocols. So you can send as a report the set identifiers that you have collected or the set of identifiers that you have produced, and there are different ways in order you can to deal with the generation of these identifiers. So these are called ephemeral identifiers. So essentially, they are identifiers that must be frequently changed. And in centralized protocols, they are downloaded from a trusted server. So the device performs an initial query in order to download, let's say, the next identifier to be broadcast. And in the decentralized protocols, the identifiers are created directly by the device. Okay, so the device creates an identifier by using, for instance, some random generation protocol and trying to minimize the duplication of the identifiers. Identifiers are kept locally in the user device, and as I said before, they are from time to time sent to the shared, to the, let's say, central memory. So from a very abstract point of view, because okay, we try to model the protocols with some abstraction steps, preliminary abstraction steps. So these contact tracing protocols share interesting features in common with extension patronets that we have worked on some years ago, both myself and Arnaud. Especially the patronets that extend with data and broadcast messages. So this observation led us to a formalization of these protocols using the families of automata with data and spatial operation that simulates broadcast communication. So this formalization can then be transformed into in the input language of the cubical model checker that is based on SMT, and that is based on an array-based language. So let's say the configuration of a distributed system is represented using an unbounded array, where each cell of the array represents an individual process. Okay. To model the memory of the individual processes, then we also have to extend this idea by introducing, for instance, multidimensional arrays. So these are the main idea. I will give you just some details on the specification language. So
you have about 5 minutes.
Okay, I will try to okay, maybe we skip some detail, but just give me some idea. So the data automata essentially are automata in which you have let's say control states, and you have finite set of variables that model the local memory of each automata. The local variables are have two types. One are first order. The first type is first order variables. So essentially they keep identifiers. And the second type of variables are second order variables, a set of identifiers. So we can keep in the memory of an automata identifiers, a finite number of identifiers, and a finite number of set of identifiers. So this is the idea. And then you have the control state of the automata. And you can also exchange messages with that are consist of both a label, message label, and data that clearly represent the data that are stored in the local memory. So we can send, for instance, an identifier, or we can copy a set of identifiers to the shared memory of the system. So a protocol is defined in this way. So you have let's say the control state, and then you have actions that represent the type of operation that you can perform during the execution of the protocol. So you can generate, for instance, a new value and store it in a variable. You can broadcast in a channel M a given variable, the content of a variable. So you can broadcast a message, and then you can be, let's say, ready to receive a message on a given channel, and the message will be stored in a corresponding variable. You can also, let's say, add a variable, an identifier, the content of a variable, to a second order variable. So you can add an identifier to a set of identifiers, and then you can also register on a given channel M that represent, let's say, one possible shared memory component, a set of identifiers that you have locally stored. Okay, so register is the operation that copies, let's say, a set of identifiers to the shared memory, to the central authority. So the global configuration consists of a multi-set of process configuration that are defined as I explained before, and then a centralized memory that corresponds to a mapping from the, let's say, the memory identifier and set of identifiers that correspond to the content of that memory. So we have, let's say, a finite number of possible shared memory components. Each one is a set of identifier, and then we have a set of identifiers within each process configuration. So the configuration of a process is a control state and evaluation of the two types of variables, and the semantics is defined accordingly to the operation that we defined before. So for instance, when you generate a new value and you store it in a variable of a local process, you assume that the variable is never appeared in the global configuration, and you simply, let's say, add that variable in the semantics of the local variables. So, for instance, if you want to add a value to a set variable, then you will do something similar. So we'll extend the evaluation of the set variable with the evaluation of the local variable, and so on. So the register operation copies a set of identifiers in a given set variable of a process into the shared memory that will be, let's say, available to all the processes. And then we also have a broadcast operation that synchronizes a subset of processes. And essentially it is that within the broadcast operation, we select a non-deterministic set of neighbors, and then we copy the message on the content of a given variable in the memory, the local memory of all these processes. So this corresponds to a very abstract model of the, let's say, broadcast communication that the device performs when is close to other devices. Okay, so we select a non-deterministic set of neighbors, and then we send the data, the certain data to all the processes. So these are the main ideas. Verification problems are we consider CounterState reachability, so verify that a global configuration that there are no global configurations that contains given error control locations, and constraint control reachability, in which we require that there are no reachable global configurations that contain a process in a given state, control state, while all other processes are in states that are control location in a given fixed set of control locations. So the second kind of property can be used to represent this kind of statement. A possible violation of the protocol of the correctness of the protocol, in which a process detects a contact when there are no positive individuals in the global state. Okay, so one process is in a given control location. The control location corresponds to the fact that it has detected contact, but there are no other individuals in the positive state. So this is called constrained control state reachability. So this kind of specification can be encoded into array-based specifications, as those provided by Cubicle. I have no time to explain the encoding, but it's in the paper. And essentially, for instance, for a global configuration, it's quite easy to implement, to encode the global memory, let's say the central authority, because we can just use an array, okay? So we can use an array for each component of the memory, and the array will contain all the identifiers that are stored in the global memory. For the process configuration, it's a little bit more complicated because we have to use nested arrays. So we have to use, let's say, bidimensional array in order to model set variables. So this is the encoding. Essentially, we have an unbounded array that corresponds to the control location and to that can be used to model control locations and let's say variables that represent individual values, and then a bidimensional unbounded array that can be used in order to encode set variables. Okay, so since we have an unbounded number of possible values, we have to use unbounded arrays in both cases. So this specification, so this encoding allows us to transform the specification into the input language of Cubicle. And in the paper, we present the results of the use of Cubicle for verifying the property of interest for the considered protocol, and some heuristics that we had to use in order to enforce convergence for the exploration strategy that has been implemented into the Cubicle model checker. And essentially, the heuristic is a combination of SMT and counting abstraction. So essentially, we have stolen some ideas from Petrnitz again in order to add some invariants to enforce determination of the symbolic state procedure implemented by Cubicle. So I conclude by saying that so in our view, so the main contribution is the specification of this kind of class of protocols. We don't know. So we had some preliminary results, preliminary formalization in the overlay paper, but we did manage to move to the practical phase of verification. So we introduced this data automata model in order to be able to apply SMT incremental model checking, and we managed to verify some interesting property for this protocol. And we, as I said before, we are currently studying decidability properties. We have some preliminary result or idea that are based on recent properties proved for broadcast protocols with data, and we hope to have some interesting result from a more theoretical point of view. Sorry for the delay, and thanks again for.
Thank you, Giorgio. Does anybody have some question for our speaker? Either people online or from Parma?
In the chat.
I cannot see the chat actually. So if you if somebody wants to talk, please just put your question to.
I skip most of the second part is in the paper. So if you're interested in the Cubicle specification, you can find it in the paper. It's detailed in the paper.
I have a question about were you able to try efficiency of this approach? Do you have some preliminary experiments, or is it just theoretical for now?
We have experiments on, let's say, on the verification task, because we perform the verification task using this tool. We don't have results on the efficiency of the protocol itself, if this is what you mean. So we have only checked some, let's say, qualitative property.
Okay, thank you.
So the property is this, the more interesting property is this constraint control reachability problem, in which you want to verify that there are no process. So essentially, it's like, so let's say the violation of this property is a configuration in which you have a process in a given state and all other processes in some set of control locations. Okay, so it's like a universal quantification over all the other processes. So this is typically these kind of properties are quite difficult to verify. So there are not many decidability results, but we have some idea. Maybe it's possible to do something for this class of protocol because for some fragment of the specification language. So yeah, but in general, these are difficult properties to verify because you have this universal quantification on the rest of the system.
Okay, I think it's time to move to the next talk that I guess will be given again by you, Giorgio, right?
Actually, no, I think that Angelo will present.
Okay.
Yeah.
Okay.
You are lucky.
Okay, so let's thank Giorgio again. And the next talk will be given by Angelo Ferrando, and it's joint work with Giorgio. And the title of the talk is Incrementally Predictive Runtime Verification.
Thanks. Can you hear me?
Yes.
Okay, let's just see if I can. Okay. Can you still see my slides?
Yes, we can.
Okay, thanks. Thank you very much. Hi, everyone. I'm Angelo Ferrando from the University of Genova. And today I'm going to talk about incrementally predictive runtime verification. This work has been done in collaboration with Giorgio Delzanno, also from the University of Genova. So I'll start just saying in a nutshell what I'm going to talk about. So we're talking about formal verification, which in a nutshell can be seen as an act of proving or disproving the correctness of some kind of system, usually algorithms, underlying some kind of system with respect to a formal specification, which is usually called a property. Application domains, usually of formal verification, consist in safety critical scenarios, which are the most interesting ones, because are the kind of systems where failure can actually be a very bad thing. For instance, they can cause death, injury, or big financial losses. And also the kind of applications where we have embedded systems. So again, systems that can be safety critical. And the nice thing is that usually are reasonably small, which is a nice thing in the context of formal verification when we can have, for instance, state-space explosion in case of static verification. I'm not going to talk about formal verification in general, but specifically to a branch of formal verification, which is called runtime verification. Runtime verification, again, very quickly and in a nutshell, is a formal verification technique that is in the middle between a formal static verification, such as model checking, and testing. So in runtime verification, we practically start from a property, from a property that is the expectation that we have about the system. And from this property, we automatically synthesize a monitor. And this monitor is nothing more than a device which is capable of observing, while the system is running, traces of events that correspond to the system execution. And when we observe these traces, the monitor is capable of telling us if the system is behaving accordingly to the formal specification. So with respect to the other formal verification technique, is not exhaustive in the sense that the monitor is not going to simulate or try to see for all the possible behaviors of the system, but only for the behaviors that are actually obtained by the current system execution. So the monitor is going to say the system is behaving correctly, but we cannot assure that it's going to always behave as we expected. Because of this, monitors are usually used both for debugging the system, so when we're actually testing the system, but also after the deployment. So after we deploy the system, we can keep the monitor there in order to check that the system is always going to behave as we expected. So there are different concerns about runtime verification, but the two that we tackle in our paper are especially related to overheads of runtime verification, because usually runtime verification monitors are lightweight components, because again are not exhaustive, so they have just to check the trace generated by the system execution, but they're still something more in the system that is running. So they are going to waste memory and they're going to waste CPU time, which is not good in the context of embedded systems where we might have available resources that can be very limited. And the second problem with runtime verification, which I called very quickly as "sorry, you crashed" problem, in the sense that, as I said, monitors are going to be there in order to check that the system is going to behave, but is not going to be good if the monitor is going to report a problem only when the problem actually raised. So for instance, if we consider a scenario where we have a monitor that is checking the behavior of a robot which is deployed in a room, and the safety specification regards some kind of safety distance between the robot and the wall, is not going to be very useful if the monitor is going to report that the robot actually crashed against the wall. It's still nice to know that, but it might be too late. So one of the points of having runtime verification more reliable and robust in this kind of safety critical scenarios is to try to add some kind of notion of anticipation. And this is usually called as predictive runtime verification, which again is a branch of runtime verification where we are not just considering events that have been generated by the system, so only the past, but only the future, but also the future. So in practically predictive runtime verification also use an additional component, not just the property, but also a model of the system, which represent an abstraction of how the system behaves. And with this information, the monitor can use the model to predict future events, and in this way conclude the satisfaction or violation of the formal property of our interest in advance. The problem with predictive runtime verification is that the model usually is manually created by an expert of the system and is not even most of the time actually available. And even in the case is available, it doesn't mean that is in the proper formalism, in the proper format that you need for being used in your predictive runtime verification tool. So in order to try to avoid the problem of actually having this reality gap of not having a model of the system, and also trying to avoid errors that might be caused by human intervention, because again, even in the case the model is present, it doesn't mean that it's going to be precise enough for us. So if the model is not correct, it doesn't cover the system as we wish, then the prediction might not be precise for us. So in order to avoid this problem, we practically decide to to create a different kind of engineering approach where we start from logs that are generated by the execution of the system. And with these logs, we are going to generate candidate models that are the models that can be used for generating events. And we do this in a loop, in the sense that we start with logs, we generate models, we use these models for doing predictive runtime verification, and then we reuse other logs in the future verification processes. So while we go on in this verification, more we know about the system and more we can be precise about the model that we generate. There are different ways to generate models from systems. We decide to go for process mining. In particular, very quickly, process mining is a software engineering technique that, starting from system executions, is capable of generating a model of the system behavior. And this is just a figure that, with an overview of the person, we start with our system, we run the system multiple times, so we have anyway logs concerning multiple execution of the system. And with these log files, we apply some kind of data mining algorithm that is going to generate for us a process mining model, which is some kind of model with expressing some kind of formalism that represents how the system behaves. With this model, we can create predictive runtime verification, in the sense that we don't need any longer to create a model or use a model created by an expert, but we can directly create a model using the information that we have about the system. So this brings us to this chain of engineering steps that we propose. This is the most general one, so it's just a high-level version of what are the engineering steps that we follow. So we start, as I said, from log files, and in the first step we apply the process mining algorithm that we choose, And this is going to generate some kind of process mining model, which represents the system behavior. After that, we might have an optional step, because as I said, the model might not be in general, also in this case, of the proper format to be used for our monitors. So we need to have this optional additional step. So the second one, where we can transform the process mining model into a predictive model, which is the one that is going to be used instead for generating the monitor. So in the fourth step, we have our predictive monitor that uses a formal specification, which is the property of our interest, and the model that we can use to predict future events. And at that point, we can just take a trace which corresponds to the current system execution and do the verification of it. With respect to the standard runtime verification, one of the most interesting aspects of this approach, of this incremental approach, is that usually in runtime verification, after we analyze a trace generated by the system execution, we just trash this trace because we don't need it any longer. Instead, in this case, since log files are actually used to create better models, or at least more precise models about the system, we don't trash the trace after we use it for doing the runtime verification step, but we add it to the set of log files that are going to be used in future iterations of this step. So this is more or less the idea behind our approach, but this is very general because I actually didn't pick any kind of formula. So up to now, practically I presented a formalism agnostic approach, but in order to be used, of course, we need to pick formalism and try to see what happens. And we proposed in the paper, and also an implementation that I'm going to explain very quickly later on, an instantiation of the general engineering steps. So as before, we start with log files, but what we are going to generate, in this case, we picked a data mining algorithm that generates directly follow graphs. Very quickly, directly follow graphs are graphs that represent information about which events are followed by which events in the traces. So for instance, if we look in this very simple example, we have two nodes, EV1 and EV2, that are attached with a transition labeled V12. This means that according to the log files, the model generated says that the event EV1 has been followed by EV2 in V12 number of traces in the log files. This is the same for the other states. That allows us to say, to know what are the relations between the events in the log files that we observed. After that, as I said, we might have an additional step or more additional steps corresponding to the second step in the general overview, in case the model generated by the process mining algorithm is not consistent with what we need at the verification level. For instance, in this case, actually happens because the tool that we want to use for doing predictive verification doesn't support natively directly follow graphs, but supports bookie automaton. So this translation has to be done. So that is what we did. So starting from the directly follow graph, we automatically synthesize the corresponding probabilistic finite state machine, which practically in this case, the translation is very similar to what we do when we go from a cryptic structure to bookie automaton, in the sense that we move the events from states to transitions. But in this case, we also add the information about probability. And this information is obtained by analyzing how many times an event actually follows another one. So for instance, in this case, we have the transitions with the tuple, event, and probability. And if we look, for instance, at the transition between S1 and S2, we have the label EV3 and a computation of the probability corresponding to that, which means in this case that the probability of observing EV3 at in that state is the probability is obtained as the number of times that we can observe the log files EV3 in that specific trace in the specific position after EV2, divided by the other possibilities. So in this case, if we look at the direct follow graph, EV2 actually was followed by EV3 and EV4. So we have two possibilities, and then the probability is computed according to that. So the probability of observing EV3 is the number of times we observe EV3 divided by the number of times we observe EV3 plus the number of times we observe EV4. And this gives us the probability of doing that transition according to the knowledge that we have extracted by system execution. After this, again, for the same reason, as I said, this is an optional step which depends on the fact, or at least it depends on which kind of predictive Runtime Verification tool is used later on. So in this case, the tool, as I said, expected booking automaton. So we need an additional change where we automatically translate this probabilistic final state machine into the corresponding booking automaton. In this case, the translation is very easy in the sense that we just remove the probabilities related to the transitions, and we set a threshold for that. So practically, we remove the probability information, but we also prune all the transitions that have a probability lower than a specific threshold. In this case, what we can say is that we are removing the transitions that are less probable to be actually observed. So according to the information that we have about the system, these transitions, these single transition in the model are transitions that can be omitted because they are like outliers, for instance, which of course depends on how many log files we had and the threshold that we pick. This is going to change the confidence that we have about this booking automata, and it can be totally customized by the user. So at this point, we generate our booking automaton, which corresponds to the information that we have about the system, and this is our model. So we can just plug it into an existing predictive Runtime Verification framework. We just pick our formalities, our property that we want to check. The model is already being generated, and we just take a trace, and we obtain the verdict regarding the corresponding satisfaction or violation of the property. As I said before, the trace after being used for the monitor is not going to be wasted, but is going to be used for populate, for increasing the log files that are going to be used in the future iterations of the approach. All the engineering steps that I mentioned have been implemented in Python, and the corresponding GitHub repository is publicly available. And here is I just reported the GitHub link if you're interested. In this specific case, just to give a bit more of details about the implementation, we used as a formalism, as a format for representing log files, we use the XES format, which is practically the standard format used for process mining techniques. And the other inputs that the tool takes are, okay, so the log files, a threshold that is going to be used for pruning outlier transitions from the probabilistic final state machine and the booking automaton, and an ATL property, which is the property that we are going to verify with the monitor at runtime, and of course the trace that corresponds to the actual and current execution of the system. So with these 4 different inputs, the process goes as I explained before. I'd like to conclude. Practically, the contribution that we presented in this work consists in a general verification workflow for the integration of process mining techniques and runtime verification in order to have a predictive runtime verification approach, which is capable of incrementally create models that can be used for predicting future events. We presented all the engineering steps, and in particular, we presented the approach in the most general way, because as you remember in the first part, I didn't actually pick any kind of formalism, but I just expressed the necessary steps for bringing from the process mining application to the predictive runtime verification application. Of course, we also needed an implementation in order to test and as a proof of concept, and this is available as a Python implementation on GitHub. For future direction, at the current level, as I said, the probability is not actually considered in the generation of booking automaton. This was more an engineering choice, because we needed to use, at least we wanted to use an existing predictive runtime verification framework in order to also show the way of using this tool with existing applications. But actually, the probability aspect might be interesting for the predictive part. So we are considering about not pruning that part. So the second step, just keeping the probabilistic final state model and use it instead inside the predictive verification in order to have a probabilistic predictive verification approach where we can use these probabilities in order to predict events. And as a second aspect that we like to study more of this aspect is related to the generation of booking automatons, because again, we just generated one booking automaton for the model when we picked a threshold. But again, we might, for instance, consider multiple thresholds, and for each threshold, they generate a different booking automaton, and then having each one of these booking automatons used to generate a different predictive runtime monitor, and then having the predictive runtime verification approach as a combination of these multiple predictive runtime verification monitors. In this way, it could be interesting to have this kind of different kind of verdicts that might be tied to the confidence level that we have concerning a specific model, which depends, of course, on the threshold that have been picked for generating that specific model. So that's it. Thanks for listening. And if there is any question, I'm happy to answer them.
Thank you. Other questions from the audience? Or from Parma, the live audience? I see a raised hand. Please speak up.
Hi. So on slide 9, can you show it?
Sorry?
Can you show slide 9 again?
Yeah, sorry.
Okay, so yeah, can you explain this arrow 3 again?
Arrow 3. Yeah, okay, no, sorry. This part, I actually skipped this part because this wasn't actually novel, because the predictive runtime verification approach that we used exists already. So practically the main idea in this case, according to the implementation, of course, we are verifying LTL properties, and the booking automaton is used to predict the future events. So practically what is done at this level as being explained in a paper from Loikers. And practically what they do is instead of just using the property and its negation to generate the monitor, they also do a product of the property and its negation with respect to the booking automaton. Practically, very briefly, the booking automaton is used to prune future events, because we know which events are going to be generated by the system, which aren't. So practically doing this kind of you just take the LTL property, you synthesize as usual the corresponding booking automaton, and then you do the product with this booking automaton, which represent the model, and at the end you just keep the same process for generating the corresponding monitor. The only difference is that now, instead of like before, you consider all the possible continuations considering the LTL property. Now you're only considering the continuations that are consistent with the model that we extracted. So are the continuations that are considering only what the system is capable of doing.
Okay, yeah, thanks. And thanks for the talk.
Thanks.
Are there other questions? Then let's thank our speaker again. And it's time to move to the next talk. The next talk is titled A Sequent Calculus for First-Order Logic Formalized in Isabelle Hall. The talk is given by Jørgen Villadsen, and it's a joint work with Asta Halkjær and Andreas Schlichtkrull. I'm sorry, I cannot really, I don't know how to pronounce the names. So okay. Please.
Thanks. So thanks for the introduction. I hope you can hear me.
Yes.
And see the slide. So until 1 o'clock, I will give a presentation of our paper. And it's joint work with Asta Halkjær and Anders Schlichtkrull and me, Jørgen Villadsen, and we are all from Copenhagen area. Of course, I assume you are familiar with first-order logic and maybe also with sequent calculus, but not so much maybe with the Isabelle proof assistant. So my agenda will be that I will say something about the Isabelle system, in particular the Isabelle Hall system, and then something about the sequent calculus and about what is actually formalized, and end with a brief discussion. So if you go to the web page of Isabelle, the first line says, what is Isabelle? And the answer is then given. It's a generic proof assistant. It doesn't say so much about how to work with it in practice, just knowing that it's a generic proof assistant. But it's like a LaTeX editor, where you also, on the fly, as you edit, you will have Isabelle proving what you are stating. So it's coming with an editor, and you online edit your document. It's a generic proof assistant, but most people will use the Isabelle Hall default system. So it's a system of higher order logic, and the first paragraph in the tutorial says that you can view higher order logic as functional programming plus logic, meaning the usual basic elementary logic. So this is a nice equation. But also going into more details, what we like about Isabelle is that it has not only the logic, the proof assistant, but it has a very large library, in particular of many data types, all kinds of numbers, lists, trees, functions, relations, sets, and so on, and also coming with state-of-the-art proof automation. But you cannot get through with complicated proofs just by the automation, so you have to write some details of the proof. And the good thing about Isabelle is that you can use declarative proofs, and that means that at any point when you move around in your document, you explicitly know, because you are forced also to state with the help of Isabelle what you want to prove, and that's at any point. So you can also, when you don't have the system installed and just look at the file, you know exactly at any point in the document what you're about to prove. And there also, what are your assumptions? And also, besides having declarative proofs, it supports structured proofs, which makes the proofs much more understandable and maintainable, such that when you change some notation or some parts of the theory, you will be able to get the proof up and running again. Okay, so a view on Isabelle is more that it's a platform, and this is explained at this recent conference on intelligent computer mathematics by the lead developer Makarius of Isabelle. And the main applications of Isabelle, in particular Isabelle Hall, but also Isabelle in general, are these formal mathematical articles or even books. So that's kind of what you're interested in, is to have these articles. For instance, also the article that we show, all the statements in our paper have been verified by Isabelle. And there is a lot of examples, many articles and books also coming with Isabelle, but the main part is now collected and for almost 20 years in an archive of formal proof, AFP, with this link. And Makarius then repeats that it's managed like a scientific journal with full formal checking by Isabelle, and also you have a high quality presentation in LaTeX as output. So looking at the archive of formal proof, the status yesterday was that we have these 6 human editors making sure that everything is fine, but then it's organized in a number of entries, and these entries are, some of them just a few pages, a small article, many like 10 or 100 pages, and also even larger books are available, for instance, thesis and so on. But you can, on a decent computer like my laptop, you can check almost all of the archive of formal proof in a few hours. There are some entries that are computational, more demanding, which are better run during the night. But almost all of them are very fast. The one we are talking about here is checking essentially as fast as you can LaTeX the document, I would say. So it's like you can simply scroll and it will be checked while you're doing that editing. Now there are almost 400 authors on this archive, and more than 3 million lines of proof and definitions and theorems. And then the number of theorems is also very high. And this number of theorems, these are the stated ones, the explicit one, not all kinds of internal small lemmas, but these are the ones the authors has actually usually also named these theorems. So this is a very substantial, and this is a view on Isabelle that it's really the platform where you have this possibility to write your articles and books. Okay, so we are describing a particular entry, so that's something you go to a web page and download. You can also browse it online, but when you download and see it in Isabelle, you can play with it, make changes, ask queries, and so on. And our entry is a sequence calculus for first logic, and our paper here describes this entry. It's a bit more than 1,000 lines, and the entry itself has these contributors, and the main author is Asta Halkjær, and it formalizes the soundness and completeness of a particular sequence calculus for first order logic, and it does it, as I'll explain later also, by using also tableau calculus, and it's based on another theory, the first order logic according to fitting theory. This is the name of that particular theory. But the actual techniques that we're using are from this particular book of Benary. I'll explain in a moment. So our entry imports another entry that does not really have a paper behind it. So there are some comments in the document, but it's not documented in any paper. But it's by Stefan Berghofer. And there, well, it goes back to a book by Fitting, and it has a natural deduction. So there's no sequence calculus, there's no tableau calculus there. And Asta contributed by the final extensions, where we also now allow open formulas that was not covered originally by Berghofer, and it's now written in declarative style. So that was not so common when Berghofer did this entry, and also other automation has been added. These are 4,000 lines, and that's needed in order to make our proof just in 1,000 lines. So the starting point for this, for our interest, is this textbook. Have it here also by Benary, standard one on mathematical logical computer science, 3rd edition now. And if you move, so it starts with propositional logic and first order logic, and when you get to page 156, you see an actual proof in the sequence calculus, written as this tree, and this is the final formula that you prove, and this then you use the rules described in the book. So this is our goal is to essentially formalize the main part of this textbook. There's no mention of natural deduction really in the textbook, but it's tableau calculus and sequence calculus. So we have, particularly I have experience for many years now teaching courses with 120 students per year, and this approach of using Isabelle in particular Isabelle Hall, is documented in this paper taken from the current paper. This reference 12, which is available online in EPTCS. And this describes the main approach, not only about this sequence calculus, but about various other systems that we have developed in Isabelle. Coming back to the sequence calculus here, I've listed the main systems. As I said, natural deduction, that was already essentially for closed formula done by Stefan Berghofer. We are doing the sequence calculus and also the tableau calculus, and the resolution calculus has been done by other people, in particular Arnaud Schlichtkrull. But for automation, natural deduction is not an option. It doesn't lead to any way to automate. And the problem with resolution calculus is that you need scholemization, you need to have clauses. So that's nicer for students in many ways to be able to work with the formulas straight on. And also the automation, the default one in Isabelle Hall uses the sequence calculus. So there's a link here, even though you don't see that directly unless you dig into the Isabelle code itself. Okay, so when moving to the main theorem in the textbook, well, it's simply left as an exercise to have soundness and completeness. The system is called G for Gensen instead of sequence calculus in the book, and it's left as an exercise. But this is only possible, makes sense, because it's referring to a completeness proof for the tableau calculus. And that's covered on many pages of these first 100 pages in the textbook. So that's you need to start with the syntax and the semantics of first order logic, and then the particular calculus, and build up the construction. And our paper does this for the tableau calculus and then the sequence calculus. Just to give some details of the sequence calculus, this is the particular calculus in the textbook. So it's a one-sided one, so you have here adding the turnstile for what you can prove. And it's grouped into some basic rules and then alpha rules and beta rules, gamma rules and delta. The gamma here, the capital gamma, is to be viewed as a kind of context. So it's a set of formulas, and the comma means that it's a set union. So we add the formula A to the context here as a set, and we can do that with multiple formulas. And for instance, the beta rule for conjunction says that if you, in some context, gamma, need to establish A and B, well, you have to branch, you have to show both A and B in the context, and that's for that. And you see for disjunction, that's the canonical one for the alpha rules. You simply split it up using the comma, which again is short for inserting A in the set, and B also in the set, starting with gamma. So gamma is just carried along all the way. It's not actively used as such in all the rules, and it's all based on having sets on the side of the turnstile here. And of course, since you have basically the set of formulas being a disjunction, you are done. Your only basic rule that are not requiring any previous proof is that when you have A and not A in any context. So that's your basic rule. So all this calculus and the semantics, of course, starting also with the syntax of first order logic, that is what we have formalized in Isabelle, and the details are in the paper. So coming to my end here for the discussion. So this formalization is, to our knowledge, the only working one in Isabelle Hall. So we are in the related work described in previous work and also in other proof of systems. But we think by far that this novel formalization is the easiest one to download. Download Isabelle, it's a one-click thing, and you download our formalization, and then you have it checked and ready to extend or work with. So we have in this way formalized a major part of this textbook, and we think there are many other systems, and we've also worked with that we should formalize such that we eventually will have all node systems formalized in a system like Isabelle. So now we have, by Stefan Berghofer, natural deduction, we have Sequent calculus, we have the Tableau calculus, we also have other entries on resolution and more advanced calculi like superposition by other authors. But just want to mention a recent formalization that we have done main work by Asta, Halkjær from, but we described in this paper that has been accepted and will appear pretty soon in this volume of the Springer Studies in Computational Intelligence, where we look at the epistemic logic, and particular modal logic with agents, and we also consider the extension to public announcement logic. And this here we have axiomatic systems, sound and complete ones, and these are available for download now in the archive, and the paper will come. But there are many more other logics to look at, so this finishes my talk. Thank you.
Thank you very much for your very interesting talk. Are there questions for our speaker? Yes, Giorgio?
Hi, and thanks for the presentation. So I wonder how difficult it is to find the right, let's say, proof strategy in Isabelle, because as far as I know, there are many, let's say, engine in the tool. So you can use rewriting, maybe Spass or something like that. So is it difficult to find the right way to prove some theorem or there are some kind of let's say user-friendly way to find the right strategy? Thanks.
For the proof like the ones in the archive, I mean, it's well known that Isabelle has quite any proof assistant would have a quite steep learning curve, but we are having many projects with students working on this, maybe for starting with propositional logic, showing particular systems being sound and complete. So it's feasible, but it takes quite some time. And when you then have the proof, you can usually spend a lot of time on optimizing the presentation and getting it very nice and elegant, and that can take a lot of time also, and usually reduces the proof size also. So I don't know exactly how to quantify how easy it is, but we have done it for many systems now.
Okay, thanks.
Other questions? I have a curiosity. It's not completely related, maybe, but I cannot avoid asking this. How do you use that in the classroom? What is your experience? Do you assign tasks or home assignments to the students, or how do you use it?
Yes, so we use it in various ways. So first, in particular, the soundness proof is not so difficult, so that I will actually in this autumn again for the bachelor students go through the soundness proof that we have here. It's less than 100 lines. But then, since the logic, the calculus has been formalized in Isabelle, the students can also then do actual proof. So I showed one, this tree structure, but making it into the format used in Isabelle, the students can have actually the proofs checked by the rules, such that we have, instead of doing a pen and paper and they hand in the proof and we have to correct it, they submit an Isabelle paper where Isabelle has checked the proof, and they get also feedback from the Isabelle system. So that's actual carrying out proofs. And then for the mainly master students, we can go into more details and also consider how to turn this abstract completeness proof into something that will actually show the completeness of a program, so that you don't have here. You will know when you have a proof that's correct, but you don't have a program that you can also extract to Haskell by Isabelle having done the proof, and that we can cover in our class. So I had an earlier reference to this paper. I think this is a good starting point if you want to know how to use it in class.
Okay, thank you very much for the clarification and the suggestions. So I think this concludes our session. The next session will start at 2:30, and so we'll meet again at 2:30. Have a good lunch, everybody.
Have a good lunch to everybody. For attendance here in Parma, there is lunch in the same room where we had coffee breaks before. And for all the other one, let's see again at 2:30. Thank you, Marco, for joining the session, and thanks to all the speakers and authors. See you later.